The fragrant Greek island of Chios, known for its ancient mastic groves and pine-covered hills, is now shrouded in ash and smoke. Since the first week of June 2025, a series of fires have merged into one of the most destructive infernos in recent memory. Driven by dry winds and record heat, this blaze has already consumed over 8,000 hectares of forests, farmland, and vital heritage groves. This isn't just a fire, it's a biological explosion, unleashing volatile compounds from trees and shrubs that transform vegetation into potent chemical fuel. In this video, we'll explore why Mediterranean wildfires burn with such intensity, how the Chios fire evolved into a chemical chain reaction, and what invisible contaminants it leaves behind. The pyrochemistry behind Chios's wildfire. Understanding the blaze, the science of fire. Wildfires are chemistry and physics at a landscape scale, representing the visible chemical energy released by volatile-rich vegetation. Every wildfire starts with an ignition, but its transformation into an inferno is fundamentally a chemical process, a redox reaction where oxygen rapidly combines with organic carbon in vegetation, releasing energy, gases, and intense heat. The precise behavior of this reaction, whether it smolders, bursts, or spirals, is governed by complex interactions of terrain, humidity, wind, and critically, the fuel's chemical composition. On Chios, wildfires are dynamic systems. Resinous pine needles undergo popcorn ignition as their volatile organic compounds rapidly vaporize and detonate, launching flames into treetops. Within thicker logs, intense heat superheats trapped water, building pressure until steam explodes outward, splitting the wood. Fire then ascends through ladder fuels into the canopy, evolving into a crown fire where entire tree crowns ignite, akin to a flashover in a confined space. In extreme cases, the immense heat and smoke generate pyrocumulonimbus clouds, fire-induced thunderstorms capable of producing lightning, downdrafts, or new fire outbreaks. Chaotic conditions can also foster fire whirls, spinning columns of flame that fling embers, igniting spot fires far ahead. This culminates in a blow-up, a sudden, drastic escalation in fire intensity and spread, driven by environmental factors, causing the fire to surge unpredictably and overwhelm suppression efforts. This makes fires in regions like Chios, and across the Mediterranean, notably explosive, a direct result of both fire physics and the inherent plant chemistry. Chios's pyrophytic ecosystem, when nature fuels the flame. The incendiary flora, natural arsonists. Chios is a pyrophytic island, where native vegetation is intrinsically built for fire. Over centuries of adaptation to drought, grazing, and recurring fire regimes, its flora evolved to store highly flammable oils, resins, and volatile compounds within leaves, twigs, and bark. Upon heating, these readily vaporize, contributing to rapid ignition, intense combustion, and even localized explosive behavior under specific thermal conditions. This inherent flammability is a key ecological characteristic. Many species here rely on fire for regeneration or demonstrate high tolerance to it. The wildfire's chemical transformation begins with pyrolysis, the thermal decomposition of plant material. For species like the Aleppo pine, Calabrian pine, rock rose, and thyme. Significant pyrolysis typically commences around 200 to 300 degrees Celsius, facilitating rapid volatile release and quick ignition. Conversely, the iconic mastic tree, resilient Kermes oak, and cultivated olive tree undergo substantial pyrolysis at a slightly higher range, from 250 to 350 degrees Celsius. All contribute uniquely to the fire's intensity and behavior. The flammability of Mediterranean vegetation is directly tied to the boiling points, vaporization, flash points, ignition by spark, and auto-ignition temperatures, spontaneous ignition, of its compounds. Alpha-pinene and limonene, common in pines and shrubs, have low boiling points, 155 to 176 degrees Celsius, and flash points, below 50 degrees Celsius, enabling rapid vaporization and ignition, driving quick flame spread and explosive bursts, with auto-ignition around 255 to 260 degrees Celsius. Similarly, carvacrol from aromatic plants like thyme, with boiling points in the 230s degrees C and flash points around 100 degrees Celsius, also ensure rapid ignition once heated, auto-igniting up to 493 degrees Celsius. In contrast, olive oil's main fatty acids, oleic, linoleic, and palmitic, exhibit significantly higher boiling points, above 280 degrees Celsius, and flash points, 112 degrees C to over 180 degrees Celsius. While requiring more heat to ignite, their high fuel content and auto-ignition temperatures, above 250 degrees Celsius, lead to sustained, hot burning and prolonged smoldering in groves. These distinct chemical profiles collectively dictate each plant's specific role in wildfire dynamics, from immediate volatile ignition to extended, intense combustion. Species profiles. Pines. The Aleppo pine, widespread at low to mid elevations, drives intense crown fires with its resin-rich needles and ladder fuels. Its resin, rich in alpha-pinene, beta-pinene, and limonene, dries fast, leading to high flame intensity and crackling, popcorn ignitions that sustain combustion with high energy release. Crucially, its resin-sealed cones only open with fire's heat, dispersing seeds onto newly cleared ground. A close cousin, the Calabrian pine, also populates these stands, storing fuel in dense branches that form a highly combustible mid-height canopy. When fire reaches their crowns, firestorms can erupt in mere seconds. Shrublands. Down in the understory, shrubs like rock rose thrive. As one of the most flammable Mediterranean shrubs, its aromatic, high VOC, thin foliage promotes fast, intense surface fires. Its adaptation includes active pyrophytic regeneration via post-fire seed germination. The mastic tree, Chiasa's fragrant yet flammable treasure. Down in the understory, among rock rose, mastic thrives. Culturally iconic in South Chias, forms woody groves that burn hot due to their resinous nature, yet regenerate quickly after fire. Among all species on Chias, none holds deeper cultural and economic value than the mastic tree, Chia, a small, evergreen shrub defining the island's landscape. Mastic resin, or tears of Chias, has been harvested for over 2 millennia, flavoring food, soothing skin, preserving textiles, and serving as ancient medicine. In 2023, mastic product exports, primarily from Chias, exceeded €15 million. Despite its immense value, this species is highly vulnerable to fast-moving wildfires. Its waxy, terpene-rich leaves, containing oils like limonene and alpha-pinene, vaporize around 160 degrees Celsius and ignite almost instantly, turning shrublands into natural accelerants that can torch fields in minutes. While mastic roots often resprout, a key survival trait, full resin production can take 5 to 7 years, with mature groves needing over a decade to recover. So while the mastic tree may survive the fire's touch, the local economy and ecosystem can suffer long-lasting consequences. When burned, mastic emits dense, aromatic smoke rich in VOCs and particulates. Its pyrolysis yields light hydrocarbons and tar-like substances, significantly contributing to air pollution and impacting local respiratory health. Olive trees, widely cultivated for centuries, also pose a significant fire risk in their groves. Their oily, brittle foliage ignites easily, promoting canopy fire spread. Due to their dense hardwood, entire groves can smolder for days, supporting sustained heat and releasing dense plumes of smoke rich in particulates. Kermes oaks demonstrate greater flame resistance due to their thick, fire-resistant bark and tough leaves, absorbing heat rather than rapidly propagating fire. However, under conducive conditions, even these robust shrubs will burn at the surface, slowly and incompletely, subsequently resprouting vigorously from their underground root systems. While less prone to explosive behavior than highly volatile species, their widespread presence makes them a significant component of the fuel load. Even the smallest species, like thyme, contribute significantly. Thyme's aromatic foliage, abundant in essential oils, quickly releases VOCs and produces dense smoke upon heating. While significant thermal decomposition of its biomass typically commences above 200 degrees Celsius, the rapid volatilization and ignition of its potent chemistry result in a fast-moving, low-level fire. None of these plants are passive fuel. They are catalysts in a chain reaction, each with a distinct combustion profile and ecological role in the Mediterranean fire regime. On Chios, the land burns not just because it's dry, but because its plants are wired for ignition. Beyond the flames, ecological and chemical fallout. When the flames vanish, their chemical footprint remains, infiltrating the air we breathe, the soil we grow from, and the waters that sustain life. As plants burn, they release more than just carbon dioxide, CO2, a long-lived greenhouse gas. They emit carbon monoxide, CO, which is toxic and impairs oxygen transport. Methane, CH4, a potent short-lived climate pollutant. And nitrous oxide, N2O, another potent greenhouse gas contributing to ozone depletion. And highly reactive volatile organic compounds, VOCs, including monoterpenes like alpha-pinene and limonene from essential oils, are also released. These VOCs, along with heat-induced no emissions, become ozone precursors in the atmosphere. Given Chios's intense solar radiation intensity in summer, conditions are ideal for photochemical ozone formation post-fire, contributing to smog and damaging both lungs and crops. Beyond gases, tiny particles, PM2.5 and PM10, escape into the atmosphere, riding wind currents across islands and seas. These fine particulates cause respiratory and cardiovascular damage, exacerbating asthma, and carry toxic compounds like polycyclic aromatic hydrocarbons, PAHs. PAHs are carcinogenic, mutagenic, accumulate in fatty tissues, and are toxic to aquatic life. Additionally, black carbon, soot, from high-temperature combustion absorbs solar radiation, accelerating snow and ice melt and contributing to global warming, often lingering for days in the atmosphere. Meanwhile, the fire profoundly alters the land itself. Ash and charred organic matter fall like snow. While ash temporarily raises soil pH and alters conductivity, and char can initially enhance carbon sequestration, these residues may contain bound toxins and significantly alter soil structure. Nutrients like nitrogen and phosphorus, released from ash and burned biomass, flood into rivers during the first rains. This can cause short-term fertility followed by leaching, leading to harmful algal blooms and oxygen crashes downstream. In some places, fire creates a hidden hazard. Hydrophobic soils. When plant waxes undergo pyrolysis, they melt and form a thin, water-repellent film below the surface. Rain then runs off rather than soaking in, triggering severe erosion, mudslides, and the collapse of stream banks. In summary, the chemistry of fire outlives the flame. It infiltrates the foundations of ecosystems, altering everything from microbial life to coastal fisheries. Nature's reaction. Humanity's responsibility. Chios Island, like much of Greece, is highly prone to wildfires, experiencing multiple significant events over recent decades. While a full 50-year wildfire register isn't readily available, the 2012 Chios Forest Fire stands out as a particularly devastating event, often compared to the current 2025 blaze. Breaking out on August 18, 2012, this fire scorched an estimated 7,000 hectares, 16,000 acres, of forest and farmland, critically damaging the island's unique mastic tree groves, the world's sole source of mastic resin. Smoke from this fire even reached Crete. While smaller, more frequent fires occur, the 2012 and current 2025 events represent major, economically and environmentally destructive incidents for Chios within the last 50 years. Understanding wildfire chemistry, from volatile ignition to pervasive contamination, transcends academic interest. It is fundamentally about our collective survival. For Chios, and ecosystems worldwide, true healing demands a profound engagement with its enduring chemical legacy. A legacy that persists in the air we breathe, the waters we drink, and the very bark of every scorched tree. If you found this analysis insightful, don't forget to leave a comment. Your thoughts, questions, or personal experiences are always welcome here. Like and share this video if you believe science can help us understand and prevent future disasters. And if you haven't already, subscribe to Chain Reaction for more in-depth explorations into the causes behind chemical, environmental, and industrial events. Thank you for watching.